Hi, my dear students. Welcome to Module 5, Lecture 1, 2, and 3. In this, we will actually discuss about the parallel architectures for nanosystems. In this lecture, we will understand how nanoscale device technology influences processor architecture and why parallelism become more essential when system complexity increases. See, the system complexities keep on increasing where the nanotechnology or nano scale devices which will actually influence the processor architecture. We will explore concepts ranging from mono and multiprocessor systems to systolic arrays, neural networking architectures, wiring delays, and nanoscale constraints. Architectural principles, mono and multiprocessor systems. See, in the coming slide, I have actually given a figure. You can actually see to that. So this is what the diagram. See, in this, uh, you can see monoprocessor architecture, which is a classical model. Okay, classical monoprocessor architecture based on von Neumann model, where memory and processor are separate. According to von Neumann model, processor and memory are separate. Memory is divided into program memory and data memory. The processor executes instructions simultaneously or sequentially. The processor executes here instructions sequentially, and performance is directly tied to instruction cycle time. When single processor performance becomes insufficient, monoprocessor systems are introduced. Multiprocessor systems are introduced. Additional processors can operate concurrently to handle computationally intensive tasks such as numerical simulations, image processing, or real-time control. This figure illustrates how processors can be arranged to work collaboratively. Again, the top two diagrams, you can see von Neumann model where program memory and data memory are separated each other. They perform sequentially and the performance is directly tied to instruction cycle time. When the single processor performance becomes insufficient, we go for the multiprocessor systems, which is in the right side B. Additional processors can actually operate concurrently to handle big tasks such as numerical simulations, real-time control, like that way. Although modern microprocessors are built on simple, elegant architectures using digital logic gates, they are extremely inefficient at the deep microelectronic level. Only a small portion on the chip is active at a time. The rest remains is going to be idle but still consumes leakage power. We can also understand from our regular devices, like a camera is actually switched on in case means okay, it have to actually shut down if you are actually going for some other applications where camera is not actually being useful. So only a small portion of the chip is actually active at a time. The rest remains idle but still consumes leakage power. This inefficiency becomes more pronounced at nanoscale where leakage power increases. Hence, future designs must dynamically power down inactive regions or transition to massively parallel nanosystems where many small processors share workloads simultaneously. So we are actually going for this kind of architecture, which are actually given in the previous slide. You can see here. not moving. Anyhow, you had actually seen in the previous slide the images below images which are C and D. Okay, so those images. See here we address the difficulty of synchronizing large processor arrays. Efficient load balancing remains a major challenge till date. Examples of modern parallel structures include systolic arrays and we can take neural networks. Systolic arrays, let's say data flows rhythmically between the processors, which is actually useful for matrix operations, DSP and convolution operations. Neural networks, if we take, it is biologically inspired systems where computation is distributed and fault tolerant. These architectures are compatible with nanoscale electronics because they rely on local interconnections and massive parallelism. So this slide mentions two important data processing structures. One is associative matrix and another is self-organizing map. This is actually a famous SAIS diagram which maps the architecture space based on how many devices each functional block requires. On the left, memory cells require only a handful of devices. On the right, an entire chip which may be required to implement a full processor. In between, hybrid computing structures which are actually coexist like CNNs, SYMs, AMs and systolic arrays. This diagram is heavily useful for identifying which architecture fits best when operating at a nanoscale, where device count and wiring density become limiting factors. Associative matrix, which is a memory structure where data retrieval is based on content rather than addresses. Associative matrix is a memory structure where data retrieval is actually occurring based on the content rather than the address. Self-addressing or self-organizing map. This is a type of unsupervised neural network which is useful for pattern clustering. These both are actually rely heavily on local connections and parallel operations, which makes them suitable for nanoscale integrations. See, considerations to parallel data processing. We now shift into analyzing the parallelism from an efficiency standpoint. Efficiency generally decreases when active chip area or clock frequency increases. Area become more, let's consider, we need to actually cover a long time, or it may, in order to switch from one place to another place, it will take some time. Consider clock frequency. The time when it get increases, obviously we will call efficiency decreases. We don't want the bus to go slowly, okay, which we have to actually go very fastly. So time should be actually less consumed one. So efficiency decreases when active chip area or clock frequency increases. If we replicate a functional block to operate in parallel or time share it, the throughput increases but efficiency does not necessarily to improve. You can actually see in the first one, yes, it's a simple architecture. The second one in the top and the third one in the top. Efficiency is almost the same even though we use several processors there or architecturals. This is because of additional wiring, multiplexing and synchronization overheads consume both area and power. Again, this is because of additional wiring, multiplexing and synchronization overheads which consume both area and power. Okay. This figure compares architectures with and without efficiency gains. The top example shows no improvement. Parallelism merely increases hardware cost. The bottom examples show true efficiency enhancement by factor n, but only when the added area and switching cost are minimal. The figure emphasizes that name duplications of blocks is insufficient. Intelligent architectural design is an essential to gain to realize the performance benefit, we can say here. Let's consider operation F, which is actually can be broken into small sub operations, which are Fi, we can say. If these are executed by independent blocks, throughput improves. However, combining partial results incurs overhead. Neural networks excel here in this case because their distributed architecture minimizes merging overhead. Pipeline architectures also benefit. Operations are serialized and executed in stages as seen in systolic arrays and fuzzy systems. Processor array topologies in this we parallel processors can be arranged in various geometrics like ring structure, cylinder structure, sphere structure, hypercubes. The topology determines communication cost and latency. Hypercubes, for example, provide logarithmic communication complexity. Additionally, parallel architectures inherently allow hardware level fault tolerance. If one node fails, the system can reroute around it. Influence of delay time. Let's see, as transistor sizes are shrinking, switching speeds improving, making clock rates in the hundreds of gigahertz is actually possible. Hundreds of gigahertz of clock rates are actually possible. However, the limiting factors shift from device switching to power distribution overhead, a parasitic wiring capacitance, signal integrity issues in interconnections. Again, I'm repeating, the limit factors shift from device switching to power distribution overhead, parasitic wiring capacitance, signal integrity issues in the interconnections. Thus, nanoscale systems are no longer limited by transistor speed but by interconnect constraints. Nanoscale devices are no longer limited by means of transistor speed but however by means of interconnect constraints. Okay, so we will see the maximum wiring length. Okay, so you can see here. This figure shows that wiring delay and distortion limit the maximum usable interconnect length. figure 6.5, you can actually see here that the wiring delay and the distortion limit the maximum usable interconnect length. As frequency increases, the acceptable wire length shrinks drastically. Only a small physical area around a driver can be reached within a single clock cycle. A small physical area around a driver can be reached within a single clock cycle. So if I am actually taking a from a long distance, so definitely it cannot actually reach. So this is about the wiring length. Despite this, high packing density still allows thousands of nanoscale devices to fit within the accessible region. High packing density still allows thousands of nanoscale devices to fit within the accessible region. That's what the wiring constraints again. Um, um, you can actually see here wiring constraints with frequency. The figure quantifies the how wiring dimensions and clock frequency influence signal propagation. As frequency values increases, the RC delay due to the wiring dominations. Wiring dominates so that the RC delay is actually happening. This limit the communication range. This is why modern nanoscale processors rely more on local computation and avoid long distance communication whenever possible. Okay. So that's what the timing sensitivity in the networks. So the it is also explaining the time delays affect not just circuits but also processor networks. Even in parallel processor arrays, mismatched timing causes misalignment data flow. Incorrect results are reduced throughput. Hence, delay management becomes essential in massively parallel architectures. If we see the 3x3 systolic array, which is given in figure 6.7 here, this 3x3 systolic array processes data. This actually processes the data in a wave-like fashion. Output emerge after 2 cycle delays because of each processing element receive and forwards data in a staggered manner. See, each, once again, you can see here these devices. See here, see this is actually after 2 cycle delay, the output is actually coming. Okay, so it is actually due to each processing element receives and forward the data in a staggered manner. This introduces latency and reduces initiation rate because both of the time is actually the same. New data can only be injected every 2 cycles unless delay compensation is actually used. You can see the delay compensation units, okay, here in the right side. See, to align the results temporarily, delay elements are inserted in the data paths. These ensure that all the processing elements produce output simultaneously, enabling consistent pipelining. Although the final output is delayed, throughput increases because new inputs can be introduced every clock cycle once the pipeline is full. Once completed, then only the new input. So this is actually about a delay of free operation via the synchronizers once the delay elements are properly inserted. Okay, so these delay elements are actually properly inserted, all outputs synchronize and subsequent processing stages can operate without bubbling or stalling effects. This greatly enhances performance and allows nanoscale systems to achieve high throughput even with the interconnect limitations. Okay. See, here we reinforces that wiring delay becomes a dominant factor in nanoscale architectures. Wiring delay becomes a dominant factor in nanoscale architectures. Designers must optimize interconnect geometry, reduce parasitic capacitance, and adopt locality driven architectural models. We call it locality driven architectural models. Global synchronization or long distance communication becomes impractical. Hence, modern architectures use distributed parallel models. We summarizes the systolic array timing challenge due to propagation delays. Outputs do not appear simultaneously. Due to propagation delays, output generally appear lately, or they are not actually uh, simultaneously appearing. Okay, output will not actually occur simultaneously. By inserting timing delays into each path, we achieve synchronized output, enabling continuous pipelined operation. Input also same time, output also same time, like that way. Although latency increases, throughput improves dramatically. This approach is essential for nanoscale processor arrays where wiring delays cannot be ignored. Thank you, students. We'll see in the next lecture.